Hello friends, so today we are going to discuss three questions, and these three questions will be somewhat out of them. These three questions, one is from projectile and other one is from, you can say, the equilibrium, or we can say bouncing ball for n number of times, and the third question is from, this one is the of our equilibrium, okay, in general. And so let us start with our first question. So it states that a small bead rests at the top smooth frictionless circular hoop of radius r fixed in the vertical plane. The bead is given a is given a very small push so that it starts sliding down along the hoop under gravity. Assume that after falling through a vertical height h, so based on this we have two questions. At what angular position on the hoop, measured from the top, is the acceleration of the bead purely vertical? Also find the magnitude of this vertical acceleration at those points. And part B, at what angular position on the hoop, measured from the horizontal, is the acceleration of the bead purely horizontal? Okay, so these are the two questions. So in this case, let's draw an approximate figure. So we are given that we are having a hoop which is some kind of circle, and it is in a vertical plane, and let us assume that C is the center of this hoop and this is our vertical axis, and the small bead initially, let us assume, is at position A, and after some time, let us suppose it is at position B, and it moves by angle of theta with respect to the vertical from the topmost point. So from here, let us draw a perpendicular from B to this on AC, and let us call this as B prime. So we know, let me draw this figure separately. So we have our A, and from A we have a C. This distance will be our radius of the circle, okay. And we have a point B, and the perpendicular distance is called as B prime, and angle is theta, and our BC will be also our R. Therefore we can say that our B prime C, this distance will be our R cos of theta. Therefore from this figure we can say that our AC is equal to R, which is also equal to our BC, and our B prime C is our R cos of theta. Therefore we can write that our distance A prime B, that is our this distance which is given in the question as h. So you can say A prime B is equal to h, and that will be equal to R minus R cos of theta. And in simpler terms, we can write take as R is common 1 minus cos of theta. Okay. So this is our fall in the vertical position of our bead A when it moves from A to B. And as it moves from A to B, let us assume that V is the velocity of this bead at point B. Therefore, we can write that for the velocity of bead at point B is V, we can use the conservation of energy. Therefore, we can say that conservation of energy, and this conservation of energy gives that the energy at A, which will be entirely potential energy, will be equal to energy at B, which will be our this kinetic energy. Therefore, we can write that our half mv square will be equal to our loss in potential energy, that is mgh, and h is our r 1 minus cos of theta, and this mass cancel out with mass. Therefore, we can write that the velocity at point B will be equal to our 2gr 1 minus cos of theta. This equation we can use later on also. Okay. And now we come to our acceleration part, and we are only interested in the acceleration at point B. Okay. So we can just draw once again the approximate figure. So this is our A point, this is center B, and this is our B point. And at B, obviously, we know that the acceleration will be in the downward direction, which is nothing but of acceleration due to gravity. And there will be two acceleration. One we can call is a centripetal acceleration, or we can say radial acceleration, that is our A of r, and other one will be our tangential acceleration, that is our A of t. And this angle is our theta with the vertical. And we can say that acceleration components on the hoop, acceleration component on the hoop and first part is our radial or centripetal acceleration, which is our A of r, and this will be equal to our v square upon r. V square we already know is our 2gr 1 minus cos of theta. Therefore, we can say that A of r will be equal to our r and r cancel out, so this comes at 2g 1 minus cos of theta. And this will be directed toward the center of the loop. Okay. So this will be center of the loop, its direction. And next will be our tangential acceleration. And tangential acceleration we can divide this g into two components. So this angle will be theta. So we are going to get this as a g over sine of theta. Therefore, we can say that tangential acceleration, that A of t, will be equal to g sine of theta. Okay. And we come to our part A, and part A states that we need the acceleration which is purely vertical. Part A, acceleration purely vertical, and this condition will be only true if the horizontal component of the acceleration is 0. Okay, so this will be true if we have the horizontal component is equal to 0. So acceleration will be purely vertical if its horizontal component becomes equal to 0. So let us draw all the respective components. Okay. So this is our start from A, this is point C, and then we having this as point B. And we know that this is our radial component and this is our tangential component. Okay. And we can divide our tangential component into two parts. And tangential component we know is our G sine of theta. So this angle is theta. So this comes as G sine of theta times cos of theta. And vertical component will be coming as G sine of theta times sine of theta. And similarly, we can write our two components for this radial also, and this angle is our theta, so this also will be our theta. So we get our AR cos of theta, and this will be coming as AR sine of theta. So these are the respective components of our the acceleration at point B. And let's find out the horizontal component of the accelerations. Okay. You can say that horizontal component of the acceleration, which suppose is represented as A of x, then A of x will be equal to the horizontal component of tangential acceleration plus horizontal component of our radial acceleration. Okay. And we already know that its tangential component as well as radial component. Therefore, we can say that our A of x will be equal to tangential component x direction is G sine of theta cos of theta, and radial component is our opposite, that is minus, and A of r is our v square upon r, and this comes as our sine of theta. And we can take sine of theta as common, therefore we get that A of x will be equal to sine of theta. We have here G cos of theta minus v square upon r. So this is the horizontal component of the acceleration. And furthermore, we can also solve it because we know that our v square r is, where it is, one second, v square upon r is our this 2g 1 minus cos of theta. Okay. We know that our v square upon r is equal to our 2g 1 minus cos of theta. So we substitute it, we get our x component is equal to our sine of theta, and this is G cos of theta minus this gives me 2g, and this comes as plus will be equal to over minus plus 2g cos of theta, and g we can take as common, therefore we get our a of x is equal to over g sine of theta. This is cos and cos, so this comes as 3 cos of theta minus of 2. So this is our acceleration component in x direction, that is our horizontal part. Similarly, and okay, we can continue here only, because like I said, the acceleration will be purely vertical if its horizontal component is equal to 0. So we are going to put x, a of x is equal to 0. So you can say a of x is equal to 0. So this gives us that our g sine of theta 3 cos of theta minus 2 is equal to 0. So obviously g cannot be equal to 0, so either we are going to have sine of theta is equal to 0, or we are going to have 3 cos of theta minus 2 is equal to 0. And when sine of theta is equal to 0, this tells us that theta is equal to 0. Okay. So theta is equal to 0, so which basically means that our the bead is at the top of the at point A, and which is very trivial. Okay, that's not possible actually. Okay, so we are simply going to ignore this part, because if value of theta is equal to 0, it means the bead is not moving from A to B. Okay. And for the other portion, we can easily say that our cos of theta is equal to over 2 by 3, or we can say that theta is equal to cos inverse 2 by 3. Okay. Now we come to our vertical acceleration at this particular point. So you can say vertical acceleration, which will be nothing but our vertical component, and vertical component is suppose represented as a of y, then we can say that our a of y, we are having two components in y direction and both are in downward direction. Okay, so that will be minus ar cos of theta and g sine square of theta. Okay, so we get this as a of y can be written as a radial component in y direction plus tangential component in y direction. Okay. And radial, we get this as our minus, radial is ar cos of theta. Ar is our v square upon r, so you can say our v square upon r cos of theta, and tangential component is our g sine square theta. And v square r is our g cos of theta, so we can just use that and take minus common, so we get our a of y will be equal to our minus v square upon r is our g cos of theta. So we can put it here, so this is minus g cos square of theta minus g sine square of theta, and we can take this as minus g as common, so this becomes our cos square theta plus sine square theta. So obviously this is equal to 1, therefore we get that A of y is equal to over minus of g. And next is our acceleration should be our purely horizontal. Part B, acceleration is purely horizontal. Acceleration purely horizontal. Okay. So for this, the vertical component is 0. Vertical component is our 0. Okay, so we already know our vertical component, that A of y. So we put our A of y is equal to 0. And therefore we get that our minus v square upon r cos of theta, this is minus v square upon r cos of theta minus g sin square theta is equal to 0. And we know that our v square upon r is 2g 1 minus cos of theta. So substituted here, we get this as minus 2g 1 minus cos of theta minus g sin square of theta is equal to 0. And g we can just, because its value cannot be equal to 0, so this comes as our I missed something. I missed cos of theta. And this whole is to be multiplied by cos of theta. So we get this will be equal to over minus 2 cos of theta plus 2 cos square of theta minus, and we have here sin square of theta. We can write this as 1 minus cos square of theta is equal to 0. And if we open, this becomes a minus and this becomes plus. So this comes 2 plus 3. So we get this as our 3 cos square of theta minus 2 cos of theta minus 1 is equal to 0. And so we need to solve the quadratic equation. And so let me provide the solution directly. It's quite simple to solve the quadratic. We are going to get either our cos of theta is equal to over 1 or cos of theta is equal to minus 1 by 3. Once again, cos of theta is equal to 1 means theta is our pi by 2. Okay, so that is, you can say, we can ignore it simply. Okay, and so this gives us that our cos of theta is equal to minus 1 by 3. And okay, so this was part B, vertical component is equal to 0, and part A was the horizontal component is equal to 0. So this completes our first question. So we come to our second question. So second question states that a ball is thrown vertically upward from the ground and rises to a maximum height h. It then falls back and undergoes repeated vertical bounces on the ground. After each bounce, the ball rises to a height equal to the fixed fraction f of the height reached just before that bounce, where value of f lies between 0 and 1. And so part A, find the total distance traveled by the ball before it finally comes to the rest. Find the total time elapsed before the ball comes to the rest. And part C, determine the average speed of the ball over the entire motion. So this is the basic question. So in this case, let us write a general formula for our, you can say, single vertical rise, motion of a single vertical rise, and from there we can just follow it for multiple, you can say, bounce. Okay. So first of all, let's write it as motion for a single vertical rise. And for that, we are first of all going to write a general formula. Suppose it starts from point A and the maximum height is of point B, and this height is suppose given as our capital H. Okay. And if V is the final velocity at point B, so obviously at maximum height, final velocity will be equal to 0, and initial velocity of projection or throwing the ball upward, suppose is our U. So we can use the basic equation of kinematics. So we can say that our V square is equal to U square minus 2GH. So our V is equal to 0. So this goes away. So we get that initial velocity of the projection will be equal to our 2GH upon of square root. And we can find out the time of rise from A to B. Okay. So you can say that our time to rise, not time of rise, time to rise to height capital H. So we are going to use V is equal to minus GT. V is equal to U minus GT, and once again final velocity at B is 0. So from here we get U is equal to our GT. U is our 2GH square root, and therefore we can write from here that time taken from A to B, or we can say time in the taking upward direction, is our 2h upon g and its square root. And obviously time taken from B to A, which is our t down, will be also equal to our 2h upon g and its square root. And total time for one up down motion, okay, let us call this as our T of H, will be equal to the summation of T up and T down. So that will be equal to our twice square root of 2h upon g. Okay, so this is the general formula of our time taken during one complete bounce, that is from A to B and coming back to A. And so now we can write the general equation for our successive heights it is going to reach. So we can say the height reached after each bounce. After each bounce. Okay. And let us assume that first maximum height is, let us suppose, small h. So it means the successive heights will be equal to h, and it is given that it's of every, you can say, height is a fraction of h, and that fraction is given as f. So that will be h, and f times h, f square h, and f cube h, and so on. So it means this is a infinite geometric sequence with a ratio f. Therefore we can say that it is a infinite geometric sequence with ratio f. And let us calculate the total distance with respect to this height h, small h rather. Okay. So the general formula we have derived with respect to capital H. Later on we are going to use it with respect to the small height, small h. So next we are going to total distance travelled. And for total distance travelled, that is for our first flight, or we can say before first bounce, and before first bounce we know that our upward distance is our h, and that is same as our downward distance. Therefore for first flight we can write this as d naught will be equal to 2 times h. Okay, that is our h plus h. And next we can write the distance after each bounce after each bounce. Okay. And so we can generalize the formula which we have already written here. Okay, and we are going to segregate it into two parts. We are just going to ignore our first part, and we are going to generalize the entire formula for this successive heights, that is fh, f square h, f cube h, and so on. So distance after each bounce, so we can say that our for bounce reaching height, and this generalization formula we can write our f raised to power n times h, and here value of n is equal to 1, 2, 3, and so on. So it means each bounce is going to have a height of fn of h, and therefore we can say that our upward distance in general for every bounce will be f and h, which will be same as our downward distance. It means total distance, let us call this for our d of n, will be equal to twice f and h. Okay, means upward distance plus downward distance. So that will be our total distance for our each bounce dependent upon value of n. Therefore, we can say that our total distance let us call this a d, and this d will be equal to our d naught plus dn. Okay. And dn is our general formula, so therefore d naught we already know is our 2h, and this general formula we can write this as our summation from n is equal to 1 to infinity, and this comes as 2h f raised to power n. Therefore, we get the distance d, this 2h we can take as common, and we get this as our 2h 1 plus summation n 1 to infinity f of n. Okay. And we can solve this summation, which is quite easy. Summation n 1 to infinity f raised to power n will be equal to our f plus f2, this is 1, 3 and so on. Okay. And this will be equal to f upon 1 minus f. Therefore, we get that our d will be equal to our 2h, and we have this as 1 plus f 1 minus f, and which we can solve it. This will be coming as 2h and f minus f, so it will be 1 minus f. So this is the total distance we traveled. And now we are going to find out total time taken or total time elapsed traveling this d distance. So you can say total time elapsed. And once again we are going to calculate the time for the first flight, and in the general formula we have taken the height as h, and this for particle solution this height is given as small h. Okay. Therefore, we can write that our t naught will be equal to our 2 square root of 2h upon g. So this is general formula for our this first flight. Okay. And for each successive bounce, you can say the time after each bounce for height. We have already generalized the formula of the height, that is f raised to power n times h. So we can write this as our t of n will be equal to our 2, and this height is our f raised to power n h upon g. Okay. So we can make a minor adjustment in this equation. We can write this as 2 square root of h upon g, and f of n we can take outside, so this becomes fn by 2. Therefore, the total time is, let us suppose, our t, and that will be equal to our tn plus t naught. Okay. So we can write our t naught is our 2 square root of 2h upon g plus, and we can generalize this equation also, that is our summation n 1 to infinity 2, one second, yeah, here 2 is missing, 2 and 2 is missing. This comes as our 2 square root of 2hg and f n raised to power 1 by 2. Now it is quite easy to solve. We can take t is equal to, this is 2h upon g, we can take as common, so this becomes 1 plus summation n 1 to infinity f raised to power n by 2. Okay. And this, you can say, evaluation of our f raised to power n raised to power 2, we can, this is basically our geometric series, and its common ratio will be our square root of f, square root of f. So therefore we can write this will equal to 2h upon g and square root of f, one second, this is our, okay, I'll write it opposite way, 1 minus square root of f plus 1, and we get from here that total time t will be equal to our 2 square root of 2h upon g, and square root of cancels out in the LCM, so this one 1 upon 1 minus square root f. Okay. So this is our total time. Now we need to find out the average speed. So we know our total time and total distance. Therefore we can say that our average speed will be equal to our v average, and this is our total distance upon total time. Okay. So we simply substitute, there is no need to solve further, we substitute the value simple. Total distance is our 2h 1 minus f, and this comes as our 2 square root of 2h upon g 1 minus 1 square root of f. Okay. If required we can solve it further, otherwise it is only depends upon the answer, what type of answer they have asked for. Okay. So this was our second question. We come to the third question, and third question, it states from a ball is projected from the ground on a horizontal surface with an initial speed v. Neglecting air resistance, determine the angle of projection for which the area enclosed between the projectile trajectory and the horizontal ground is maximum. So this is a, you can say, basically we are going to find out the area under this curve in this particular question. And you can just solve this question by using the sum of the equation directly also, like trajectory equation, but we will drive it and then we can take it from there. Okay. Therefore, let us draw an approximate figure, and this is our velocity v, angle theta, and it is going to have two components, our v of x and our v of y. So we can write that our v of x is equal to v cos of theta, and our v of y is our v sine of theta. And if the horizontal distance is traveled is our x, and the vertically it travels the distance of y. Therefore we can say that our horizontal distance x horizontal distance is our x, which will be equal to our v cos of theta multiplied by time t. Okay, so time t is taken to travel the horizontal distance and same time will be taken to travel the vertical distance. So we have a horizontal distance and then we can write our vertical distance. Vertical distance y will be equal to our v sine of theta minus half g t square. Okay, and this is our time t. And from our horizontal we can write that equation for our time. So we can say our t is equal to our x upon v cos of theta. Therefore we can say that our y is equal to v sine of theta x v cos of theta minus half g, and this comes as our x v cos of theta whole square. And we can simplify it. This v and v cancels out. Therefore we get that our y is equal to our x tangent of theta, and minus this comes as our g x square. We get this as 2 v square cos of theta. And we know that it travels from point A and our till point B. So it means this projectile is going to land at B when value of y is equal to 0. Therefore we can say that projectile lands at B when y is equal to 0, other than x equal to 0, because x will be also 0, but we are talking about the landing point only. Okay. Therefore we put y is equal to 0, so we get 0 is equal to our x tangent of theta minus g x square 2v square cos of theta. And so in this case we can solve it further, and we can take x as common, and x cannot be okay. So we take x as common, so we get this as tangent of theta minus jx 2v square cos of theta is equal to 0. So obviously x cannot be equal to 0. Therefore we get that our tan of theta minus gx 2v square cos of theta is equal to 0. And from here we can find out the total distance traveled, which is nothing but our range. We can put r later on, and this will be coming equal to as our 2v square cos of theta tangent of theta divided by g, and this is nothing but our range. Okay. And we can put tan of theta as sine and cos, so cos goes away. Therefore from here we get our range is equal to v square upon 2, and one second, I missed something. I missed a square and square. So this left with our 2 sine theta cos theta, which will be giving us sine 2 theta. Okay. Now we are interested only what? That is area under the trajectory. Okay. So we are interested in area under the trajectory, and that is basically area under the curve. So we can see A, and 0 to R we have here y dx, that is similar to our area under the curve. And we already know equation for our y, therefore we can write that our A will be equal to our integration, and we have 0 to R, and this is our x tangent of theta minus gx square 2v square cos square of theta and times dx. And now it's a simple integration. So we are going to integrate our first part, and the first part is going to give us x square, tangent of theta is our common, so we get this as our r x square by 2, which will be giving us our r square by 2 tangent of theta, and then we are going to get x cube by 3, and this will be giving us our 6 minus g upon 6, and this comes as our r cube and v square cos square theta. So this is our total area under the curve, but we have to find out the maximization of this. Okay. And we already know the value of our range, that is sine of this v square by 2 sine of 2 theta. Okay, so everything will be in theta, so we can easily derivate then it with respect to theta, because we have to maximize area for a particular value of theta. Therefore we substitute value of range, that is our r, so we get area is equal to, this comes as 1 by 2 tangent of theta, and we have this as v square upon g sine 2 theta whole square minus this is g, and we have 6 v square cos square theta, and we have our cube, that is our square g sine 2 theta, and this is our cube. Okay. And so we can just sort it out, and we get this as v4 by 2g, v square by v raised to power 4 by 2g, and this comes as our sine square 2 theta multiplied by tangent of theta, and this comes as minus, so we are going to get this as v raised to power 6, and we have v square, so this will be giving us v4, so we can write this as our g, and g square we can also cancel. Okay, let me write this as v4, and we have our sine cube 2 theta divided by 6, and this comes as g and g cube, so we are left with g square, and we have cos square theta. Now we can further say that our sine 2 theta is equal to sine theta cos theta. Okay, that is solve it. It will take a little bit of time, but it is quite easy. So we have v4 2g, and we have this as sine 2 theta will be giving us sine square theta, and this will be coming as 4 here. Okay. So this is sine square theta cos square theta multiplied by sine theta upon cos theta, and minus v raised to power 4 sine cube theta divided by 6 g square, and we have this as cos square theta, and square goes by cos, so we get this as sine cube theta. Okay, we can take it as common, so ultimately we get this as our area A will be equal to our 2v4 divided by 3g square, and this will be also square, otherwise I think the rest is okay. So this gives, we get a 3 by 2 v4 g square and sine cube theta times cos theta times cos theta, and we need to maximize, so we are only dependent upon this function of theta. So you can say maximize the area and we can say that our area A is proportional to our sine cube theta and cos theta. And so we are going to assume this is a function of theta, f of theta, and we are going to derivate it. So we can write that our function f is equal to sine cube theta times cos theta, and their derivative with respect to our theta for maximization will be giving us 3 sine square theta, and sine is our cos, so this comes as cos square theta, minus cos is sine, so this comes as sine 4 theta. And obviously we can say for this is equal to 0, and we can take our sine square theta as common, so we can say that our sine square theta, so we will left with 3 cos square theta minus sine square theta is equal to 0. And so from here we can say that our sine square theta is equal to 0, or 3 cos square theta minus sine square theta is equal to 0. So the first term is going to give us that value of theta is equal to 0. So we are going to simply ignore this part, and we are going to solve the second one, which gives us that this will be basically our 3 cos, and this will be our tangent square theta is equal to 3, or we can say our tangent of theta is equal to square root of 3, and therefore value of theta is equal to our 60 degree. So for this value of theta, our area will be maximum, and we can put value of theta into the equation of our area. Here we can say that our area maximum will be equal to our square root of 3 v raised to power 4, and this is our g square, and we get this as our 8g square. So this is a maximum area that for particular value of theta is equal to 60 degree. So what we found that for a projectile, if the angle of the projection is of 60 degree, then the area under this trajectory will be maximum, which is our A max. Okay. So we've also found out value of A max as well as our angle, that is our theta. So these were the 3 questions for today. Thank you.